then when it's time to use the video, I'll let you know. Okay, good morning everybody. Need your attention up here, please. Andres, go ahead and take your seat. No. There's a chair over there. Go ahead and put that chair back. Okay, so yesterday we learned about the volume and surface area of spheres, and we're going to start off by practicing a few problems. Who can remind us of the formula for the surface area of a sphere? Angelica? Uh-huh.
It is 4 pi.
4 pi r squared. Okay, go ahead and turn and talk with your table. How does 4 pi r squared relate to the video that we watched yesterday about the tangerines? Talk at your table. How does it relate to it? What about the tangerine video? Do you remember it? No, when you filled the tangerine? Okay. Natalia, can you share with us what you said about how it's related to the video about the tangerines? Okay, yeah, when it fills, when you peel the tangerine, it fills 4 circles. So we have 4 pi r squared for surface area of each sphere. And then what was the formula for volume of a sphere? Pi r cubed. So with this one, we just have to be extra aware that we're cubing the radius instead of squaring the radius. So go ahead and get started, and we'll go over the answers in about 3 minutes. Do all 4. That's the full diameter, so what do you need to substitute? So what would that be? Yes. Would what be 9? Radius? Why do you say that? And 18 is the? Tell me what type of solid is this? What is it called?
So raise to 4 times 9.
Okay, what'd you say 9? It says 18.
The whole thing is 18.
Okay, what do you mean by the whole thing? What's that called?
Diameter 18.
Okay,
The radius is 9.
very good. Why would you divide it by 2? You already divided it by 2 here, though. if you divided it by 2 again, you would be only finding the volume, or the surface area of half of the sphere. Okay? But except for what units do you need to put? Centimeters what? Yep. Okay. Okay, so let's really quickly check to make sure we know what all the radii are. I don't mind if you hold that as long as it doesn't make any noise, okay? Thank you. So what's the radius of number 1? 9. What's the radius on number 2?
12.
It's 12, good. Okay, how about the radius on number 3?
6.
6. How about the radius on number 4? 8, okay. And our volumes and surface area, what did you guys get for number 1 surface area? Who can tell us? Milan?
1017.876 centimeters squared.
Okay, glad we have our units centimeters squared. We have 1,017 and 876 thousandths. Snaps if you got that. Okay, how about number 2? Who will tell us the answer? Andres?
1,809.
1,809 and
5574.
Maybe get the one.
Never mind.
it's okay. You can always have
Meters.
more than 3 decimals. That's fine. Meters squared. Okay, snaps if you got that. Okay, volume. Who will tell us what we got for this problem here, Luis Enrique?
904.779
Okay,
miles squared. Cube.
nice catch. Miles cubed. Snaps if you got that. Okay, and number 4, we have a volume of, who will tell us that one? Yes, Yvonne?
2,144 and 669
Okay, good. Well, the only thing I want to add is we want to say 661 thousandths here. Excellent. Okay, snaps if you got that one. Okay, thanks to all of you for volunteering your answers. Go ahead and look at the back. We're going to start off with our exploration, but before we do our exploration, we're going to talk about some vocabulary. And we are going to be using the beach balls, but they're our great tool. We are going to be able to draw on the beach ball with this marker later, so when it asks you to put points on the sphere, you actually are going to draw points on the sphere. But let's make sure that we keep a hold of the beach balls and they don't go flying around, because then you will not be able to learn as much, because we'll have to go track them down. Okay, so the first thing I want to talk to you about is a new vocabulary word, which is antipodal points. So everybody go ahead and say antipodal points. Okay, the definition of antipodal points is they are 2 points that are on opposite sides of a sphere. There are 2 points that are on opposite sides of a sphere. The easiest 2 points for you to see are probably going to be this top one here that looks like a circle, and this bottom one on the other side where we blow up the beach ball. Those are antipodal points, but they're not the only antipodal points. These are antipodal points. These are antipodal points. Okay, so you're going to be able to find, like if Daniel chooses 1 point, choose any point on the sphere. This one here. Okay, I can find an antipodal point. It's just going to be the point on the opposite side of the sphere. And the line segment that connects the 2 antipodal points, anybody have an idea of what that's going to be called? Imagine a line segment in between these 2 points. What would that be? I see diameter. I was like reading your lips, Angelica, and then I said diameter. Okay, Angelica just said diameter. Okay, this would form a diameter. Okay, so here's what I want you to do quickly. I want you to turn and tell your neighbor what antipodal points are. Ready, set, go. Okay, y'all seem to understand what antipodal points are. Now what I want you to do is take a moment to talk with your neighbor. How many sets of antipodal points do you think exist on a sphere? How many sets of antipodal points? Just take a guess. How many sets of antipodal points do you think exist on a sphere? Talk about it with your table. Love it. You guys agree with that? Okay, so if I said this point. Ah, very nice. Okay. Do Do y'all have any guesses that you want to throw out there for the number of sets of antipodal points? 3. Mizzy says infinite. I hear a few other people are saying 3. Are there any other guesses besides 3 and infinite?
6.
6. Okay, so we have 3, 6, and infinite. 10. Okay, so we have 3, 6, 10, and infinite. I want you to snap with the one that you agree with. Who thinks there are 3 sets of antipodal points? Who thinks there's 6 pairs of antipodal points? 10? Infinite? Okay, so I'm hearing a lot of snaps for infinite. Would anybody be willing to share with us why they think so strongly that it's infinite? Andres?
I feel like it's infinite because like it's a sphere, it's a circle, and basically you can choose any point you want, and you can basically like not make it up, but like any
Find
point.
the other out.
Yeah. And when you cut it, it'll find its own.
Like the
Okay.
little orange.
Uh-huh.
that cutting.
Oh, okay, like when you peel the orange, okay, you can keep peeling into smaller and smaller pieces. So the surface of the, so that's telling us that the surface of the sphere has an infinite number of points. And then what Andres said was that since you can choose any point, you can always find its opposite point, so we can keep doing that again and again. Okay, snaps if that's making sense to you right now. Okay, so what you're gonna do for this exploration is it says, draw.
So was it?
It is infinite. Yeah, give yourself a pat on the back if you said there's infinite numbers of pairs of antipodal points. Okay, we're going to do part 1. I stack up here. Today we're going to be exploring the differences between 2 different types of geometries. You might be like, what? There are 2 different types of geometries? I never got to learn about this in high school. I didn't learn about this till I got to college, so you all are really lucky. All year we've been studying what's called Euclidean geometry. I want everybody to say Euclidean. Euclidean, and you might be like, what is that about? That's a strange word I've never seen before. Well, it's named after an ancient mathematician named Euclid. What was his name? Euclid. Just like we have the Pythagorean theorem was named after, do you guys know? The Pythagorean theorem was named after Pythagoras. So a lot of these math terms are named after the ancient mathematicians that discovered them. Euclidean geometry is based on ideas from Euclid. So one more time, how do I say this word? What? Euclidean. Okay. Spherical geometry is everybody say spherical geometry? Spherical geometry is a new kind of geometry that has some different rules than the geometry that we've been studying all year. So what you're going to be doing now is you're going to be comparing Euclidean geometry here, label it with an E, with spherical geometry with an S. So in Euclidean geometry, you're going to be labeling points right here on your piece of paper. So you can be drawing your points like here on this piece of paper. Whereas spherical geometry, you're going to be drawing your points directly on the sphere with your marker. Okay? And once you draw the points, you're going to describe what you see when you connect the points. Okay? And I have a word bank for you right here. Small circle, great circle, line, line segment, arc, radius, diameter. So there's a lot of words for you to pull from when you do this exploration. Okay? So when it asks you to draw on the paper, it means just draw right here. When it asks you to draw on the sphere, I don't mean the picture of the sphere, I mean the actual beach ball. Okay? So go ahead and get started, and we'll come back together in about 4 minutes. Just this piece of paper. Just draw any 2 points on that piece of paper.
So that's the mid diameter.
Okay. So we want to, first step, draw 2 points on the piece of paper. Anywhere on the piece of paper. Not on the sphere, but on the paper. Just pick a point and draw it. Yep. Label it C, and then label another one D. You want to just draw. What did you create? When you connect connect two points, don't think about it as a circle. I shouldn't have drawn that circle up there because I think y'all are thinking about it as a sphere. I was just trying to show you where on the paper you can draw your points. So just think about this, the path from C to D. What is that?
Wait, the
Just look at C and D. Yeah, can you be more specific? What goes in front of segment? A line segment, yeah, a line segment.
I'll put line segment right here.
Okay. Do we have our point C and D? Just go ahead and put a point C and a point D anywhere on your paper. C and D, then connect them. Now you should be talking about what did you just create when you connected those points.
Still then?
So the space between C and D, that pathway, what is that called? Line segment, excellent. Now, if you were to extend that line segment infinitely, what would it create?
Oh, you gotta draw?
To take a right, but a line itself is infinite, so you don't have to put the word infinite in front of it. A line just means it extends both directions forever and ever. If you extend it, originally it was a segment. When you extend it, it's a line. Go ahead, now you should be moving on to part 2 where you're actually putting points on your sphere. So you take a line segment and you extend it infinitely in both directions. What is that going to create? Just think about it on a piece of paper. So you have a segment, like you have a little segment, like look at this crack right here on the table. That's a segment, right? You extend it forever and ever in both directions. What is that now? It's a line. Good. So now y'all are ready to put your points with your expo marker. Okay, down here, all your points here. You're going to use these points. Certain these? Okay. Okay, so what path exists between these 2 points? What would you call that? A line segment? How is it different at all from this, from drawing it on the paper? How? Yeah, like if you were to look at it this way, what do you notice about it? Curve. Can you think of a word or look at a word bank with a word that describes that path a little bit better? How are y'all doing? Good. Did you draw the points on your sphere? Did I take your sphere? Y'all should have told me a long time ago. Here's some points that have already been drawn in there. You can draw new points. Hector, go ahead and put them on the table, okay? I don't want to fly away. Okay, take 30 more seconds. Oh, so just connecting these 2 points. What have you created now? A line segment? On the sphere, it's something else. What do you think? Let's look at it from the side.
You're infinite, man. You said
From here to here. What does it look like from this perspective? What? A curve, okay. Check out your word bank. Do any of those words in your word bank do you associate with this like curved piece right here? An arc. What do you guys think about that? Does this look like an arc? Yeah? Awesome. Now the next one, can you extend this infinitely? Forever and ever? Okay, let me watch. What happens? It stops. Okay. We're going to go ahead and go over what we have. Okay. So we had 2 points on our piece of paper, C and D. So here's an example. C and D, what have we formed when we connected them? Line segment, excellent. When we extended infinitely, what have we created? A line. Good. Okay, let's look at part 2. This is when we were talking about a sphere. So we have our 2 points and we connect them. What have we created? A line segment. I hear a line segment. Any other ideas? Does everybody agree with that one? Okay, I hear a line segment. I hear a radius. Max? I hear an arc. How is Yvonne has a question. How is it an arc? Max, can you explain your thinking about why it's an arc?
Did you look at it from the different angles from the side? On the side.
Isn't that called arcing?
Angelica has a question.
Isn't it called arcing?
Isn't it called arc length? Good question. So it's kind of different. Okay, let's all focus up here. So Angelica's question is, isn't that called arc length? There's a difference between an object and the length of an object. So this object itself is called the arc, and the arc length is like how long is it if we measured it, okay? Do you guys see how this is an arc right here? Yes, okay. It's really helpful to look at it from this perspective because when you look at it straight on, you're right, it still does look like a segment, but if you think about it from this perspective, you can see that this is an arc. Now last question, can you extend this arc infinitely?
Yes. No, you can't because, well, actually you can.
What happens?
It's gonna become an end.
It's going to become an end point because it's going to either come back all the way around to where it started from, or if you try to extend in both directions, your fingers are going to meet up on the other side, on the antipode, right? Okay, so can it be extended infinitely? No, but if you extend it all the way around, what are you creating? If you extend it all the way around, you're creating a great circle. You're creating a great circle. Okay, one more thing I want to mention about great circles. There are a lot of different great circles that you can create. So all you need to think about when you're creating a great circle is, are you cutting the sphere in half? If you're cutting the sphere in half, you're creating a great circle. So you could do this a lot of different ways. As long as you're cutting it in half, you're creating a great circle. Tell your neighbors how you create a great circle. Okay, I like what Angelica just said. She said, I thought that's called a hemisphere. So a great circle and a hemisphere are related to each other. So imagine that I cut this sphere in half, okay? The rim that would be created around it, that's a great circle. And then the actual 2 halves, those are called hemispheres. Okay, see the difference? Okay, so the last thing we're going to explore together has to do with the differences of a triangle in Euclidean and spherical geometry. So in Euclidean geometry, it's just the kind of triangles we've been talking about all the time. They're flat. And tell me, if I add up the 3 angles in a triangle, what do I get? Talk with your neighbor. What do I get if I add up the 3 angles in a triangle? Okay. I haven't heard anything else except 180. So now what we're going to do is see, do you think that's going to be the same or different on a sphere? What do y'all think?
Different.
Same or different? Does anybody think same? Okay, I just need to find my protractor. Here we go. Okay, so if I come up to you, I want you to tell me how big the angle is. Do y'all see this triangle here?
Yes.
Yes, okay. So we're going to start off here. So tell me, how big is that angle? 80 degrees. I want you to write that down. It's 80 degrees. Write this down as 80 degrees. Okay, now we're going to do another angle.
Oh, wait.
Can you say it a little bit louder? 50 degrees. So we have 80 degrees, we have 50 degrees. And now we're going to do one more. Y'all hear that? 65. Okay, so I want you to add up those three values. We have 80, 50, and 65, and what'd you get? 195. So is that the same as a triangle, a regular triangle on a plane? No. Is it less than or greater than a triangle on a plane? Greater than. Okay, so I know we only did one example, but in spherical geometry, all the triangles on a sphere are going to have a sum greater than 180. Okay, greater than 180. So if you thought they would be different, you were right. Okay, we're going to practice using some of our vocabulary right now, and we're going to read this as a group. Before we get into it, I just want to go over a couple words, make sure we know how to say them. Everybody say Euclidean. Euclidean. Spherical. Okay, so you're going to read this out loud, starting with the person that's sitting furthest to the left-hand side of the room. So if you're the furthest to the left at your table, you're going to read out loud first. Okay, if you're the furthest to the left, you're going to start reading first, and then you're going to work your way around the table with every single sentence. If there's only two of you, you're just going to go back and forth every single sentence. On your mark, get set, start reading. Continuing the two corresponding grades, saying the two corresponding grades. Okay, sounds like we're about done reading. So Euclidean, do you have a question about this?
It's not about this, it's about.
Okay, so Euclidean, we'll save other questions for later. Euclidean geometry is based on a what? The surface of a what? A flat surface called a plane. Whereas spherical geometry is based on the surface of a sphere. Okay? In Euclidean geometry, we have a line. In spherical geometry, that line becomes a what? A great circle. Excellent. And then lastly, in Euclidean geometry, if we have a segment, that segment becomes what? This is the one that Max was talking about. That segment becomes a what? The arc. Okay. So this just summarizes some of the main ideas in that paragraph. Here on your notes, you have a little comparison between the angles in a triangle. So in this side, we have Euclidean geometry. You see that the angles of a triangle equal to what? 180. Whereas here, in spherical geometry, the angles of a triangle equal greater than 180. They're going to be greater than 180 degrees. Okay. So let's look at the difference in a specific postulate. It says, tell whether the following postulate in Euclidean geometry is also true in spherical geometry. Okay, so can I have somebody read this postulate right here for us?
I read it.
Missy?
There's a line and a point not on the line there. Then there's exactly one line through the point parallel to the given line.
Okay, so if there's a line, you can go ahead and draw this on your paper. If there's a line and a point not on the line, do you guys agree that this point is not on the line?
Yes.
Then what must be true? There's exactly one line through this point that's parallel. Do you agree? Any other line I draw? Any other line I draw is not going to be parallel. Okay, so what we want to do is we want to see, is this true on a sphere? Okay, So first thing we can do is we can replace every place we see line with what term? We're getting closer, great circle. So if there is a great circle and a point not on the great circle, then there is exactly one great circle through the point parallel to the given great circle. So we want to see, is that true or is that not true? If it's true, it means that that postulate is going to be true on spherical geometry, and if it's not true, then it doesn't work for spherical geometry. Okay, so if there is a great circle, okay, do y'all see this great circle that I drew around this direction? Yes, okay. So here's our great circle, and I want to pick a point that's not on that great circle. So, Giovanna, can you add a point that's not on that great circle? Not on this great circle right here? Okay, so Giovanna added this point. Y'all see it?
Yes.
Okay, can I draw a point? Can I draw a great circle through this point that's going to be parallel to this one right here?
Yeah.
What do you guys think? Yes? Okay. Where do you think it would go? Okay. So Angelica and Yvonne are saying, wouldn't it touch? If it touches, is it parallel? Okay, so what was their question?
It wouldn't touch from it would touch the circle. I didn't know which is.
It would touch this circle?
So it would be like that.
Okay, yeah, so if we drew a circle here, if we drew a great circle here, would it intersect with this great circle here?
Yes.
So would they be parallel?
No.
No, okay. Okay, so what we just talked about over there is if we were to draw a great circle through this point, it would intersect this other great circle. It's impossible to draw a great circle through this point that would not intersect this great circle. The reason is all great circles will intersect each other. Okay? All great circles intersect, so this is not going to be true. Why is it going to be not true?
Because all great circles.
All great circles intersect. Good. Okay, I want you to take 2 minutes with your group to just write a little bit. How is a line in Euclidean geometry different from a line in spherical geometry? Take about 2 minutes, and then we're going to do another example. Okay, I enjoyed reading what you guys had to say. We're going to talk about, is everything okay? Okay, we're gonna talk about one more example right here. Okay, so in Euclidean geometry, there is exactly one distance that can be measured between any 2 points. If I have 2 points here, there's one distance that can be measured, like this. On a sphere, there are 2 distances that can be measured. So if I put 2 points, Kishan, can I get you to put 2 points on the sphere? Just anywhere. Okay, so we have these 2 points here. There's 2 distances I can measure. I can measure from here to here. Can you guys think of a different way I could measure it?
Yeah,
Max?
yeah.
All the way to the other side.
You could go all the way the other side. Think about it this way. If we're here, and let's say we wanted to fly on a trip to China, we could fly in one direction and get there, or we could fly in the other direction and get there. And one way might be shorter than the other. So if this segment from here to here is an arc, we've created an arc on this side and an arc on this side. Which one of those is the major arc and which one is the minor arc? Who can tell us, who can describe a little bit for us which one's major and which one's minor? Which one's major, which one's minor? Angelica?
The major one is the one that goes all the way around, the minor one is like it touches.
Okay, excellent. What do you guys think about that? Agree? Yes? Okay, nice. So we're going to practice finding the distance, and we're going to be finding, remember earlier Angelica was talking about arc length? We're going to be finding the arc length to find the distance between the 2 points. So, it says the diameter of a sphere is 15 inches, and the measure of arc AB is